All right, so in the previous one, we're busy with momentum and force. In the previous video, we saw that force is related to momentum, but it is the rate, the time rate at which momentum changes. If the rate, if the time interval over which the momentum changes is large, then the force is small. If the time over which the momentum changes is small, then the force will be larger. Okay, that's just kind of an intuitive kind of description there. Now, another thing we want to look at is that the direction of any force is the same as the direction of the momentum change. So force is a vector, and it has direction as well as magnitude. Direction as well as magnitude. Okay? Now, let's now look at this example, and this will allow us to look at when multiple forces are acting on an object. Okay? So imagine pushing a crate in a straight line along a surface at a steady speed of 1 meter per second. Okay? What is the time rate of change in the momentum of the crate? What's your answer? What do you say here? Well, if there is no change in velocity, no change in speed, then there's no change in momentum. Your delta P is 0. And if there's no change in momentum, then there's no change in force, resultant force. So, but how can this be? Okay, because you are pushing the crate. But how can the change in momentum be 0? The reason is because there are actually two forces. There's the force that you're applying to the crate, and then there's also the force of friction. There's also the force of friction. So let me just try to find it. Here we go. So you're applying a force to the crate, and at the same time the table is applying a friction force to the crate. So the crate is experiencing two forces, the force by you and the force by the table. And as long as these two are equal and opposite, well, the friction force is generally always opposite the direction of motion. As long as this is happening, then your change in momentum is 0 because you have a constant velocity. Okay? So, let's consider this here. It says, before we just considered a single force acting on an object, okay, and that is equal to the time rate of change of the momentum of that object. But now, what happens if that object is interacting with more than one other object? Okay? Then the resulting effect on A's momentum is due to the combined action of those forces. And we consider the principle of superposition, which is the vector sum of the forces exerted on A is equal to the vector sum of the rate of change caused by A's momentum by the individual forces. So here we go. The vector sum of all forces exerted on an object equals the time rate of change in the momentum of the object. Okay? All we're saying is that we find the resultant of all those forces, and it's equal to the time rate of change of the momentum. So let's see if we can look at this one and try to do it. Imagine pushing a crate initially at rest so that it begins to move along a floor. Initially at rest, and it moves along a floor. Okay, so in A, while you are setting the crate in motion, increasing its speed, okay, in the desired direction of travel, what is the direction of the vector sum? The vector sum. Remember, you can add vectors up, right? So, if you've got, I hope this works. If you've got a force there, F1, and you've got another force there, F2, and you add them up, then the vector sum of these two would be 0, right? Because it's that one plus that one. That is the vector sum. If you add these two forces, F1, F2, the vector sum will be that. There's your vector sum, okay? So, what is the direction of the vector sum while you are setting the crate in motion, increasing its speed? Well, let's see. If you've got the crate, you've got this force that you apply, okay? And you've got the friction force here, okay? F friction, right? There's two forces acting on the block, on object A. And if it's increasing its speed, then this, let's call it F applied. FA minus F friction is going to be your vector sum, and it's going to be pointing in that direction. Okay? So it means that if you add up these two vectors, you're going to have a resultant vector pointing in this direction, which means that if there's a force, a resultant vector sum of force, then that means that there is an increase in speed in that direction. Okay. Suppose you suddenly stop pushing and the crate slows to a stop. While the crate slows down, what is the direction of the vector sum of the forces exerted on it? Well, we know that it would be to the left, because it is slowing down. There's no longer a constant velocity. There is no there's no more force by you on the crate. There's only a force by the table on the crate. So that's why there would be a force here, and it's moving to the right, but there's a force to the left, which means it's slowing the crate down. Oh dear. Now I need to find where we were. Okay, I'm going to stop here and continue in the next video.